Well, welcome back after an extended break. I hope you all got rested. I hope you're all staying safe and you're ready to get back to work. I have spent the last 4 hours screwing around trying to get some software together that's going to work. And I think I found it. I had a bad microphone. I got a microphone that echoes. I finally found a microphone that doesn't echo, and on and on and on. So, what we're going to do is we're going to have lectures, and then in the middle of the lecture sometime, I'm going to ask you to go to Canvas and do a short quiz on the material that we are covering. This is to encourage attendance. Most of you did the quiz on Monday because I wrote it down on the pad. There were a lot of people that did not submit the quiz, and I can only assume that they were not watching. Maybe they've dropped the class. I don't know. In that vein, you should all know that the university has modified some deadlines, and you all are perfectly within your rights to drop this class with a W. You don't get a refund, and if you drop it with a W, of course, you're not going to get any credit, and that could impact your financial aid status. So I would talk to your financial aid advisor before I did that. You also can, and by the way, I think you can drop with a W almost up to graduation, end of the semester. So if you're interested in that, because this is not your cup of tea, then you can take that route. Also, the deadline for changing from graded to pass-fail has been extended. I think to the end of April, but I'm not sure. Check on that too. Again, pass-fail may have implications with your financial aid, because financial aid requires that you maintain a certain GPA, and with pass-fail, you don't get any GPA enhancement. Okay, I think that's enough in the way of housekeeping chores. Let us go on now and review a little bit about what we were doing before the break. So in order to do that, I have to change to this really nifty document camera that the department bought for me. Unfortunately, the software that I have available to me right now is kind of crude, so that means I have to close my webcam, then switch to the document camera. So we're going to see whether or not I can do that. Okay, close the camera and open the document camera. Look at that. Now here's another change that I'm going to make. Instead of using the whiteboard, well, I'm actually using the whiteboard, but it's down there. Instead of using the whiteboard, I'm going to go with a piece of paper and draw on it with a pencil. It doesn't smear, and it's got a finer line, so I think it will be better for all things considered. Okay, before the break, we were talking about virtual memory. Now, in a traditional address mapping system, what we have over here are the addresses that the CPU generates. These are the addresses that a program would manipulate and would then send out. So this is kind of the address bus, if you will. It's all the stuff in between the CPU and the physical memory over here. So traditionally, a program generates an address for a byte. And that address comes over here, and it references a single byte of physical memory. Now, this is straight one-to-one mapping. Every byte over here has a byte over here. And this is the third byte in the program's address space. Notice that that references the third byte in the physical address space. And this byte in the program address space references essentially the same byte over here. So what we have is basically the program sees a representation of physical memory. We talked about the limitations of this. You can't have a larger address space over here than you actually have physical address, that is memory. It basically requires your compiler, your program, to know how much physical memory there is over here so that it doesn't generate addresses outside of that. And that's just not good for a modern computer system. So we go to virtual memory, or virtual address mapping. Now, in a virtual address system, we still have programs over here that are generating byte addresses, and we call that a virtual address. And those virtual addresses go through a mapping process which the operating system oversees, and this mapping turns these addresses in the virtual address space into addresses in the physical space. So these are physical addresses. So a byte address is generated, and that is mapped into a location on the disk that has nothing to, well, I don't want to say it has nothing to do with it, but it's not the same location. Here the third byte is being mapped way down here, and nothing is mapping to the third byte in the physical address space. So we now have the ability to save data in the physical memory in a location which is not the same as the virtual address which references that. So that gives us that ability, but since these are still byte addresses, that means that we have to have a translation entry right here for every single byte in physical memory. Well, where do you suppose these mapping tables are kept? Well, they're kept in memory. And so each one of these entries in the mapping table is going to require more memory. How big is one of these? Well, it's got to be big enough to contain an address, which means that it's probably bigger than a byte. So let's just say that each one of these entries is 4 bytes. It's a 32-bit system, right? Well, that means that we've got to have 2 to the 32nd entries. That's an entry for every byte of physical memory we have. That's assuming we have 4 gigabytes of physical memory. We'd have to have 4 billion entries, 4 giga entries here. And each one of those entries is 4 bytes long, so that means we got 16 gigabytes of map, but we've only got 4 gigabytes of physical memory. I mean, this is insane. We're using 4 times as much memory to do the mapping as we actually have to hold the data. Well, heck, if we got that much memory, why don't we just say, oh, look, we've got 20 gigabytes of memory over here, and forget about the virtual mapping process. So doing this byte to byte is not the best way. So what we do is we divide up the virtual address space, we partition it into what we call pages. Now these pages represent a contiguous block of virtual address space. So let's just, for the sake of argument, say that we chose a page size of 4K. That's 4,096 bytes in each page. Now this decision is made by either the CPU designer or the OS implementer, but it's not anything that you as a programmer have anything to do with. I mean, this is a fixed number and you can't change it. So if we've got 4K pages over here, what we're going to do is, instead of translating bytes, we're going to translate the block, the page. So we're going to take physical memory over here and we're going to divide it up into identical sized pieces called frames. And the key is that the size of one page is exactly the same as the size of one frame. So I can map this page into that frame. That frame holds exactly one page because it's the same size as the page. So if each frame holds exactly one page, then I can map where the frames are stored. Now, if I do that, and we have a 4,000 byte page size, then that means I have reduced the amount of memory that is necessary to hold the translation tables by a factor of 4,000. I've reduced the size of the translation tables by 4,000, which is quite a bit. So let's see what happens now. If I've got a 32-bit address system and I've got a full 4 gigabytes of memory installed in my machine, and let's just say that I divide that up into 4K chunks. Well, a 4K chunk, 4K means that you have to have 12 bits to address each an individual byte in a 4K block. You need 12 bits to do that. So that means that 12 bits of a virtual address have nothing to do with where the page is. Those 12 bits only have to do with where the byte we're looking for is within that page. And we don't have to map that. We're only mapping the page. So we start with 4 gigabytes. That's 2 to the 32nd. We can ignore 12 bits. So that means that 2 to the 32nd divided by 2 to the 12th, because that's the page size, gives us 2 to the 20th. That means that there are 1,000,000 pages. Well, actually, it means there are 1,000,000 frames over here in the physical address. But if we've got a 32-bit virtual address space also, it means that there are 1,000,000 pages. So now we, instead of trying to map 4 billion bytes, we're only trying to map 1,000,000 pages. So that means we got 1,000,000 entries, potentially 1,000,000 entries in the page tables over here. Now, if each one of those is 4 bytes wide, like we were talking, that means that we're using 4 million bytes to hold the pages. And since we've got 4 gigabytes, that means that we're only using 1,000th of the amount of memory we actually have to hold the page tables. And so it's considerably more conservative of memory. But, and here's a big but, when we have multiple users or multiple tasks, I don't want to say multiple users, when we have multiple tasks, each task has its own set of page tables, which means that you've got 4 million bytes of memory to hold page tables for each task. And so if you've got a lot of tasks, you fill up your memory pretty quickly with just page tables, and there's no room left for anything else. So in order to solve this little problem, we're going to introduce, I guess we're not ready to introduce that yet. What we've got here is a this is a diagram that shows the mechanism used to translate a byte address from over here to a byte address over here. So here is a virtual byte address. Here is the physical byte address. Now, the least significant, in our case, 12 bits, which are used to locate a byte within a page, those same 12 bits can locate that byte within a frame because frames are exactly the same size as pages. The byte offset within the page does not have to be translated because the byte offset within the frame is exactly the same because the frame holds the page. So the page number is the only thing that needs to be translated. So page numbers 0, 1, 2, 3, 4, 5, 6, so if you've got page 97, that goes in here. That is used to index into entry number 97 in the page table. What we find in that location is the frame number. The frame number has the byte offset from the virtual address appended to the least significant end of it, and we're back to a 32-bit byte address, but this is a byte address in physical memory. So the page number is used as an offset into the table, and the table then provides a frame number, and the byte offset is stripped from the virtual address over here and it's glued onto the physical address over here. Okay? So this is a diagram essentially of that exact same mechanism. The page number is used to choose an entry in the page table. The content of the page table entry is used to supply the frame number. The byte offset from the virtual address skips the translation mechanism and goes directly over here and supplies the byte offset for the physical address. And it just hums along. Now, because multiple tasks each have their own set of page tables, we can get lots and lots of page tables, and we could very easily use up all of our memory just for page tables. So we're going to introduce another concept called demand paging. Now, in demand paging, we have to have a storage system out here, and I'm going to use a disk drive for that storage system. The operating system controls the demand pager through an operating system service called the pager, or the page manager, depending on how you want to look at it. So what happens is, if the operating system determines that it needs to free up some memory for some purpose, it can choose a frame that it doesn't think is being used efficiently, and we'll talk about that in a second, chooses a frame, and it copies all of the data that's in that frame. In other words, it copies the page over here to the disk drive in a file. It's called the virtual address file for this task. Each task has its own virtual address file, and that file contains a complete image of the virtual address space. Every virtual address that this program has ever generated is in that virtual file, and the value that should be stored in memory at that address is also stored in the virtual file. Now, only a portion of the virtual address space that is stored on the disk is actually in memory at any given time. When a program first begins, the operating system gives it an initial set of frames. It's going to get a frame to hold some code, and it's going to get a frame for some stack, and it's going to get a frame for data. And I don't know how many frames you get is a setting that the operating system controls. And we don't know what it is, and we don't really care, other than it's what we got. Now, you can ask the operating system to increase the size of your working set, but there's no guarantee that the operating system is going to agree to do that. So, the only choice you have if you need more memory is to take one of the frames from your working set and move it over here to the disk drive, thus freeing it up, and the operating system can then take another page from your virtual space that is presumably stored over here and move that into the newly freed frame. So if the operating system, but this is not something that you do. You don't say, hey, I want to move this frame into the virtual file and then bring this other frame or this other page in here. That's not something that you do. You just generate an address. And if that address belongs to a frame, let me rephrase that. If that address, if that virtual address that you generate belongs to a page which is not currently in memory, in other words, the page is over here on the disk drive someplace, if that's true, then the operating system will halt your program. Basically, you'll be marked as I/O bound and you'll lose your time slice. And while others are running in the background, the pager will choose a frame from your working set to be swapped out. And now there are two different kinds of frames at this point. There are clean frames and there are dirty frames. A clean frame is one in which the data that is being held on the hard drive in the virtual address file is identical to the data that is being held in memory. Now that might be that would almost certainly be true of code, because code doesn't change. So a page that is stored in a frame that contains code, that page is going to be identical to the same page that's being stored out here on the disk drive. That's a clean page. If you choose a clean page to be swapped, then you don't have to copy it to the disk, because the disk already has the proper copy of that page. The other kind of frame or page, of course, is dirty. Now, a dirty frame is one in which something has changed. We've written a value into that frame, which means that the values that are in memory for that page are different from the values that are being stored in the virtual file for that page. In that case, if that's the frame that the pager chooses to swap out, then the contents of that frame do have to be written to the virtual file on disk so as not to lose the change that was made to memory. So if the operating system has a choice, all things being equal, it will choose a clean frame to swap out, because then it doesn't have to write or save the data to disk. There are lots of ways for the operating system to choose which one of the working set frames it wants to swap out. You can look at which frame has been used the least. So in order to do that, you have to have some counters to keep track of how much a frame is used. Those counters would be over here. And so this entry gets wider. It holds not only the frame number, but it's also got to hold a counter that keeps track of how often this frame is referenced. Another way to do it would be to find the frame that has been referenced the least recently, meaning it's the oldest one. It hasn't been referenced in a long time, let me put it that way. if it hasn't been referenced in a long time, probably doesn't need to be in memory. So these are some of the strategies that the operating system might use to choose a frame to be swapped out. But anyway, when it's necessary, a frame gets swapped to disk. And so now we can have essentially an infinite number of page tables for an infinite number of tasks. And those page tables and the frames that a reference, most of them live out here on disk. Only a small percentage of all of the tasks pages are actually in memory at any given time. So we have a combination now of virtual address translation and demand paging. Well, for an individual task, we could have lots and lots of pages. I think we said the page table would have 1 million entries in it. Well, that's a really big table. And for reasons that will become apparent here pretty quick, what we're going to do is we're going to limit the size of a page table to 1 page, whatever the page size is. In our case, the page size was 4K. So that means we're going to say, all right, no page table is going to be bigger than 4K. Now, if each of the entries in here is 4 bytes, that means that there's 1,000 entries. That means this page can translate 1,000 page numbers into the appropriate frame numbers. Now, let's think about that for a minute. 1,000 pages at 4,000 bytes per page is 4 million bytes. That's a pretty good sized program in terms of code and data and all of that. And a lot of programs will run with a single page table. It's not a big deal. However, some programs require lots of code or lots of data or both, or code and data that's scattered all over the place. And so a page table would not be enough because, don't forget, this is page 1, here's page 2, page 3, page 4. We get down here and we've got page, what would it be, 1023, since there's 1,000 entries in here. And those represent contiguous addresses in the virtual address space. Well, it's possible to generate addresses beyond that, of course. And so you would then need another page for the next 1,000 entries. And so what we're going to do is we're going to say, well, heck, why do we keep all of those pages in memory? I mean, I could have a lot of pages, and most programs wouldn't use anywhere near all of them. So, keeping this in mind, we're just going to expand this demand paging idea one step further, and we're going to say we need a master page table, and the master page table points to one of the many possible page tables that we could have in our virtual address translation system. So the master page table, now we're going to take this page number field over here in the virtual address space. We're going to partition it into 2, not necessarily equal sized. And the most significant part of the virtual address space is going to be used to index into the master page table. So this is, where's page table number 0? Where's page table number 1? Where's page table number 2? Where's page table number 3, etc., till we get down here. Now the master page table is also 1 page in size. And so, assuming it's got 4 bytes per entry, which isn't a bad assumption for our little machine, This could handle 1,000 pages. Page tables, I'm sorry. The master page table can point us to 1,000 page tables, and each one of those page tables can point us to 1,000 frames, which means that taken together, we can now translate 1 million page tables into frame numbers. The middle entry here is the page entry. That's used to index into the page table. So what we get out of the master page table is essentially the address of the beginning of this page table. This tells us which entry in that page table we want. So basically, there might be some scaling involved here, but we basically just add these two together. That gives us the address of this entry. Now, coming out of here is the frame number, and then we get the physical address. So this is a two-layer virtual system. And since we now have a master page table, we can page the page tables, because the master page table can keep track of whether a specific page table is in memory or paged. If the page table that this virtual address is referencing is not in memory, then we have to get I/O bound again, let the operating system swap the desired page table into memory, update the entry in the master page table to say it's no longer on disk. And by the way, this field in here where it normally gives you the address of the page table, if the page table is not in memory, then that same field is basically a location in the virtual address file for where to find it. Okay, so now we can page the page tables. I don't know this for a fact, but I would suspect that every virtual address translation mechanism has a minimum number of page tables that it keeps in memory, 2 or 3, something like that. But if you exceed that, then you can certainly page one of them out and bring in another one. All right. That's about as far as I want to go with this right at the moment. Since we've started talking about the disk drive and storing stuff on it, I thought this would be a good time to talk about disk drives and how they work. So we're going to do this from 2 different points of view. We have the physical and we have the logical points of view. In other words, how do we describe a disk drive from a physical point of view, and then how do we describe a disk drive from a logical point of view? So that's what we're going to do. We're going to start with the physical point of view. A long time ago, in a galaxy far, far away, the first disk drives that were available for consumers to use consisted of a disk, isn't that clever the way they named it, a disk of flexible mylar, which is a plastic, and it is essentially indestructible. If you've ever tried to tear a piece of mylar, you'll know what I'm talking about. Mylar is really tough stuff. And they coat the surface of the mylar with a magnetic coating, very similar to what you would find on magnetic recording tape, if any of you still have your cassette recorders or your 8-tracks or your reel-to-reels or anything like that, or very similar to what's on a VHS tape. So it's coated with that. Now, there's a hole in the middle, and a spindle goes through that hole and clamps onto it to spin it. So when it's in operation, of course, the disk is spinning. Now, from a physical point of view, data is stored on this thing in concentric tracks. So there's a track. Now, like an audio recorder, there is a record head. And this record head is driven by a motor of some kind. Usually it's a stepper motor, because you get real precise control from stepper motors. But the stepper motor moves the head in and out. That's the only movement it has, is in and out. In actual fact, the head is probably mounted on something that pivots right here, and the motivational force is right there, so this thing swings in and out like that. But it doesn't really make any difference. You can think of it as moving in and out like this. So the motor's job is to position the head precisely over the track so that the data that is stored on that track can be read. And as the disk spins underneath the head, the electrical impulses, or the magnetic field on the disk creates electrical impulses in the head, because the head's nothing more than an electromagnet. And we get an electric current that comes out, and we can convert that into ones and zeros. So we've got all of these concentric tracks. Probably should label those. Track. And I don't want to draw them all in, but you know, they're all in there. Okay? Now the original floppies were 8 inches in diameter, and they held about a megabyte. They were called Shugart floppies. And you know, the first consumer computers that came out, what we would recognize as PCs, were really for business. And these drives were pretty good sized physically. They're 8 inches in diameter. By the time PCs became available to the common man for personal use, the size of these things had shrunk to 5¼ inches. And that's the one that I'm most familiar with. In a 5¼ inch, you got 40 tracks labeled 0 through 39. And the entire disk held 360 kilobytes. Not a whole lot by today's standards, but it was certainly enough back then. Because if you didn't have one of these things in your system, you were storing your programs on audio tape. And let me tell you, that was a pain. Because generally speaking, you had to play the cassette back on exactly the same machine that you recorded the cassette in order for it to read your data error-free. So even if they were small, 360 kilobytes, they were darn well worth it. Okay, so we've got all this data on a track. How do we find the data? Well, in a floppy, there was another hole. And underneath was a light source, and on top was a light detector. And as the disk spun, that hole would come around and for a brief instant would allow light through it, and the light detector would recognize it. That's called the index hole. And the signal from that light detector indicated the beginning of the track. So if you draw a lateral line out here, that's the beginning of that track, that's the beginning of that track, that's the beginning of this wavy track. And every track, the beginning of the track was in the same line, along that same line right there. So this thing's spinning along. We get a pulse out. The disk controller, which is driving this whole thing, sees that pulse and says, okay, now we're ready to read. Well, just to be sure that the head is over the correct track, the beginning of every track, I guess this thing is spinning in clockwise direction, the beginning of every track contains a header, and the header contains some stuff in it, but the most important thing it contained in it was the track number. So the track number came off as data from the header, and the disk controller would look at that track number and compare it to the desired track number and say, oh yeah, we're right on, or oh no, can't read this, got to move another one in either that direction or that direction. Also in this header there was a fairly long space, I guess you could say. I think there were 32 bytes in there, and those 32 bytes were just, they didn't mean anything. I think they were A5 or maybe they were AA. Anyway, I think they were alternating bits. It could be 55 or AA. I don't remember which, but that produces alternating bits, 10, 10, 10. And when you look at the electrical signal that results from that, and you know the speed, you can calculate what the frequency of that signal should be, and you can use that to you could use that to adjust the speed. That's not how they did it. The reason those things are there is very simple. The electronics were very slow, and you read a track number. That track number has to be digested by the electronics, compared to the desired track number, and a decision made about whether this was the correct track, and the electronics just weren't fast enough to do that before the actual data had rotated under the head. And so this represents time for the track number to be digested. Interesting, huh? Okay, and then comes the data. Well, the data was not one continuous string around the track. The data was divided into equally sized chunks called sectors. And a sector held a fixed amount of data. That was part of the definition, or the geometry, if you will, of how this worked. And so, for example, a sector might hold 16 kilobytes. Now, the reason that there are sectors rather than just one long continuous track is that the disk controller, when it transfers information to and from the disk, always transfers it in sector-sized quantities. It doesn't go in and fetch the individual byte that you're looking for, because it doesn't have that fine of motor control. So all you do is you tell it, hey, give me all the data in that sector, and then I will pick out the byte that I want. Now this is the disk controller saying that. So the disk controller says, give me all the data that's on that sector, and I'll worry about finding the exact byte that the customer wants. If you didn't divide this into sectors, then the minimum amount of data that would be transferred between the disk and the disk controller would be an entire track, and that would be very, very time consuming. So in an attempt to keep the time for transferring to a minimum, it's divided into sectors. Now, each sector has a header that says, this is sector number 0, this is sector number 1, whatever. And so, in order to find a particular piece of data, you have to know what track and what sector it's in. And we'll worry about how you know that later. The disk controller sends a track and sector number over. That moves the head to a particular track, and then we wait for the disk to rotate until the desired sector rotates under the head. Now, each sector has a header that tells you what sector number it is. It's also got some space in there so that that sector number can be digested by the disk controller to determine whether this really is the sector that we're looking for. And so, assuming that it is, the data that then follows the sector header is read, stored in a buffer somewhere in memory, and then the operating system is told where that buffer is, and the operating system picks out the part you want, and then it gives it to you when your program restarts. Now, here's an interesting fact. We talked about the electronics being slow. If this is sector number 0, and the amount of data that you want to read is larger than one sector, you would think that this would be sector number 1, and you could just read from here and then keep reading over here. But the electronics are slow, remember, and that wasn't possible. So what happened was they would use this entire sector here as breathing space, because I just read 16,000 bytes of data here, and I've got to stick it in memory, and that takes a long time. So this isn't sector 0. And in fact, this isn't, I'm sorry, sector 1. This isn't sector 1 either. On the original floppies, 2 sectors were skipped before you got to sector 1. And then 2 more before you got to sector 2, and then 2 more before you got to sector 3, and then 2 more before you got to sector 4, and then 2 more before you got to sector 5, and 2 before here's 6, and here's 7. Now that worked out very, very well, and I have to say that I didn't plan it. But sectors need to be, you need to have an odd number of them so that as you go around, it all works out. This is called 3-to-1 interleaf. Three-to-one interleaf. That's because the electronics were slow. Now, if you had 2-to-1 interleaf, you'd only have to skip 1 sector before you got to the other one. On modern machines, always 1-to-1 interleaf. In other words, there's no interleaf anymore. Sector 1 will follow right after sector 0, etc., etc. But on the original ones, this is how it was. And so, the disk controller is told, give me all of the data in sector 4, track 32. And the disk controller's job is to position the head correctly, wait for the platter to spin to the right location, and then transfer the data. That's all there is to it. Some interesting things. Since each sector is a fixed size, and it's not always that size, that is an example. That means that this sector on the inner ring holds exactly the same amount of data as this sector on the outer ring. Now, this sector is linearly longer. I mean, if you took a ruler and measured it, it would be longer than that one. So that means that the data is sparsely spread out here and densely packed in here. And that's true. And the kind of coding that is on the disk basically defines how dense you can store the data. So if you got a new coding that was twice as good, and that means you could put twice as much data on in this little space, that means you could put twice as much data everywhere. You actually could probably put 5 or 6 times as much data in this sector because it is so big. But to keep things simple, all sectors are the same size. Let's see, what else? All right, now, this is probably going to sound weird. What happens if you need a volume, that is a drive, that's larger than that? I guess I need it back again. Well, there are several things you could do to increase the amount of data that's stored on this thing. First of all, you could get a better coding that allowed you to do it more densely. That's true. You could put more tracks on. That means shove the tracks closer together. Well, that means you have to have a better coding that's able to get the data more densely. So we already talked about that. But it also means that your read-write head has to be smaller so that it doesn't cover 2 or 3 tracks at the time. It means your positioning mechanism, the motor, whatever it is that you're using, sometimes it's even a voice coil that's used, but your positioning mechanism has to be that much more precise. But that is certainly one way that you can get more data on here. Now, dividing it up into more tracks isn't going to give you more data, because the concept of a track is sort of man-made. It has nothing to do with the physical reality of the disk. However, as you can imagine, you're going to reach limits on all of these things. So what happens, or what happened, was some bright person said, hey, okay, here's the floppy. We're looking at it edge on now. So here's the read head. Okay, that's a head. And the data is stored on this. Some bright fellow said, this is the spindle that drives the whole thing. Okay, some bright fellow said, why don't we store some data on the other side? I mean, we've got another side here that's not doing anything. It's basically the same as this side. Why don't we code it, put another head, and then we've got twice as much data for the same size floppy. And that's exactly what they did. Went to 2-sided floppies. The heads are tied, not electrically, but mechanically tied together so that they move in and out at the same rate. So the 2 heads are always over the same track, one on the top, one on the bottom. But if it's track 22 up here, it's going to be track 22 down there, because they move in tandem. Electrically, of course, they're different. The signal coming off of this head is completely different from the signal coming off of this head. But usually, well, on a floppy, always, you don't read both heads at the same time. The data was stored on the top surface until it was full, and then you started storing on the bottom surface. Well, now, in order to locate a particular piece of data, you have to know whether you're going to use head 0 or head 1. So to find a particular piece of data, you have to know the head number, the track number, and the sector number. Those 3 pieces of information have to be passed to the disk controller so that it knows how to position the heads and what sectors to read. So that's sort of the physical way a floppy drive works. Now, rotating magnetic hard drives work essentially the same way, except they usually have more than one platter. The platters are all driven by the same spindle. Each platter has a pair of heads to read the data. So here we've got head 0, and here we've got head 7. The platters, instead of being made out of mylar, are made out of aluminum. They are hard. The aluminum is coated with magnetic material. Now, we can get much denser recording on a hard drive than we can on a floppy, for a couple of really good reasons. The hard drives are sealed. They operate at much tighter tolerances than a floppy drive. The air that is passed over a hard drive is filtered, whereas on a floppy drive, they're removable, and you have to work with a lot bigger tolerances when things are going to be moved around. If you look at, let's go back to the floppy drive here. On a floppy drive, these heads, when the disk was reading and writing, these heads were in actual physical contact with the surface of the floppy. And as a result, there was wear. The heads, were scraping along the surface of the disk. And that would wear the disk out. So what they did was they put a timer in the operating system, and 5 seconds, well, let me back up. When you want to read or write to a floppy, the motor comes on. Now that means that the first time you read or write to it, not the first time, but when you read or write to it, you have to wait for the motor to speed up to 300 RPM for a floppy, 300 RPM. That takes a while. Then you can actually start looking for the data, and you find it. Every time you access the floppy, a timer, a 5-second timer, countdown timer, begins. And if you do not re-access that floppy within that 5 seconds, the motor will shut off to prevent wear on the floppy. So if you access the floppy and then 2 seconds later you access it again, and then 3 seconds after that you access it again, and then 4 seconds after that you access it again, the floppy stays on continuously during all of those accesses. 5 seconds after the last access, it shuts off. Now compare that to a hard drive. In a hard drive, there is a space in here. The head does not touch the surface of the platter. That means you can squeeze the data in there a whole lot more densely, because you're not going to be physically abrading the surface of the these are called platters, by the way. It's a platter. So a platter has two surfaces, surface 0 and surface 1, which correspond to head 0 and head 1. And you can talk about platter 0, surface 0. And then platter 0, surface 1. And this would be platter 1. This is its surface 0. And then it has a surface 1. Whereas the heads are, from a global point of view, they number from 0 down to 7. So all you need is head, track, and sector. Those three things are all you need in order to find it. Now, I said that there was a space here. The distance, let me make a blow up. Here's the head, and this is the surface. here. This distance right here, the smaller you can make that distance, the more densely you can pack your data, because the data, there's a magnetic field around the data, and the strength of that magnetic field is directly proportional to the strength of the current that's going to come out of the head, and the closer you can get it there, the more current you can get, and blah, 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 blah. So this distance right there. Now, what is that distance? Well, I saw once upon a time this is the oil from a fingerprint. Okay, so on some surface, at whatever scale we're looking at, that's the oil from a fingerprint. Okay, this is like dust. Okay, here's the head. Actually, there's another one over here, which is a hair. A human hair is just gigantic compared to these other things. So you can see that this distance is extremely small. Now the question is, how do you get a head to reliably maintain that distance? Well, it's kind of clever the way they do it. The head actually has wings on it. And these wings, the head is aerodynamically shaped. And as the disk rotates, and it rotates very quickly, a floppy ran at 300 RPM, your hard drives, slow hard drives, are 5400 RPM. Most people have got 7500 RPM. Some people have got 15,000 RPM hard drives. But as the hard drives rotate, they create a torrent of air, currents of air, and these currents of air actually fly this thing. And so it literally flies above the surface. If this head ever comes in contact with the surface, it's what we call a crash. And you all know that disk drive crashes are not good, because it will destroy part of the platter. This head should never come in contact with the platter. There are two ways that the head does come in contact with the platter, two common ways. The first is if you lose power and the disk stops spinning, well, the lift for the head is going to be gone, and as a result, it will slowly crash in. Well, that was solved by having power disruption circuitry built into the disk drive. The instant that power is cut to the disk drive, the heads are immediately pulled back as far as they can be. And back there is a wedge. So there's two heads, and they get pulled back. Here's the platter, and over here someplace is a wedge, and when these things get pulled back, this wedge kind of keeps them separate so they don't smash into each other either. So that's power failure recovery. So you don't see heads crashing from power failure anymore. That's pretty rare. However, vibration can do it. These distances are so small that vibration can do it. If you were to drop your laptop while the hard drive was reading and writing, it could crash. And there are limited things that you can do about that. You can, try to insulate your hard drive from vibration and all of that, but you can always drop it off of a taller building. So that is not foolproof. But that's how you get so much stuff on a hard drive, is by putting the head so much closer to the surface and maintaining a controlled environment. So let's go back to this. This is what a hard drive looks like. This will be a 4-platter hard drive. Now, we got 8 heads, and we can fill up the first surface, and then we can fill up the next surface, and then that surface, and then that surface, and that surface, and that surface. In other words, treat it like a great big floppy drive. Or we could do other things like we could store bit 0 on platter 0, bit 1 on platter bit 0 for head 0, and bit 1 for head 1, and bit 2 for head 2, etc., etc. And a byte is then stored on the hard drive like this. Each surface stores 1 bit of the byte. That's one way of doing it. There are lots of ways of doing it. Some of them have to do with error detection and correction, that sort of thing, what we call a RAID. You might want to store your bits in different places like that. Maybe one of these platters doesn't store any data at all, but it stores information about how to recover data if it's ever necessary. It's an advanced form of parity. We talked about even and odd parity when we were talking about the CPU. Parity is a form of error detection. Now, in the simple parity schemes we talked about, there was no error correction possible, just detection. But in other detection schemes, you can correct for some errors. But that always requires that you store more bits. Not more data, but more bits. Some of the bits describe the data in different ways, but they don't contribute to the data. There's one mechanism called the Hamming code. And the Hamming code allows you to detect 1 and 2-bit errors. If you remember, the simple parity could only detect 1-bit errors, because a 2-bit error, the second error, didn't correct, but it masked the first one. But in a Hamming code system, you can detect 1-bit errors, and you can detect 2-bit errors, and you can correct 1-bit errors. But the price you pay for that is, for every 4 bits of data, that is, for every nibble that you store, you have to store 3 additional bits of code detection and correction. So you've almost doubled the amount that you have to store in order to get the error detection and correction. So that's how a physical hard drive works. Basically what we have is we have this model. Here's your program, and you ask the operating system to do something with a file, to read a file, open a file, whatever it is that you're asking. Now the operating system is going to ask the device driver, it's an E, device driver, and the device driver is going to talk to the disk controller, which talks to the disk. I have been describing what goes on between these two. Okay, the geometry on the disk, basically head, track, sector. The disk controller knows what the disk is supposed to do and tells it to do that. The data that comes off of the disk the disk controller usually has its own buffer to store that. And then it copies that data back over here. Now, what comes off of the disk is not pure data. There's all kinds of stuff in there, as I've said. There's headers, there's footers for each sector. There's a header and a footer for each track. Well, that's not part of the data. So the disk controller strips those off, and it takes, it makes sure that it's over the right track and it's over the right sector and all that kind of stuff. It doesn't just throw it away, but it doesn't pass it on. What gets passed on here is the pure data. And it's also not obvious what the actual data is, because you're not going to get back just ones and zeros. You get back signals, that sort of look like this, and from the relationship of these signals, the disk controller decides whether that was a 1 or a 0, and it sends it to the device driver. So it's fairly complicated. Now, the rest, well, I guess I should say, this part over here, this was the physical. This part over here is the logical. These components of the system view the disk drive logically, not physically. So over here, we don't know anything about surface, head, track, sector. And that's what we will talk about next time, is how do we logically view a hard drive, and how do we access the information that is on it. Well, we've got a couple of minutes left is all. On Wednesday, that's tomorrow, we will talk about the logical view of a hard drive and go on our merry way. Still have not figured out how we're going to proctor exams. At least one member of the class does not have a webcam. Seriously considering, having your mother come watch you take the exam or something and swear her in as a proctor. I don't know what we're going to do, but we'll do something. We'll do something here eventually. So it's me again. That's it for today. We'll see you all tomorrow. So you guys take it easy. Bye.